Hello and welcome everyone. This is Shilpa Jain from PS Modern College of Engineering, Pune. Today's topic is Introduction to Partial Differentiation, a very powerful tool for understanding optimization problem. Let's dive into the world of multivariable calculus. Let's start with the basic question. Why should we study partial differentiation? Think about it. Many real life function depends on multiple variable. Because, for example, temperature depends on location and time. Profit P depends on price and quantity. Pressure P depends on volume and temperature. So, unlike school maths with only one variable and real world system are multivariable, we want to understand the effect of one variable at a time. Partial differentiation allows us to see how function changes with respect to one variable, keeping others constant. It's used everywhere in physics for studying thermodynamics, wave motion, heat flow, in engineering for studying stress strain analysis, fluid mechanics, in economics for calculating marginal cost and marginal profit. So what is exactly partial differentiation? See definition. It is the method of finding rate of change of function with respect to one variable while keeping other variables constant. It's a key technique in multivariable calculus and form the foundation for optimization modeling and analysis in many fields. See f of xy, mathematically see f of xy equal to 3x square y plus 7y, then dabba f by dabba x means partial derivative of f with respect to x, keeping y as a constant. So here dabba f by dabba x is 3x, derivative of 3x square is 6x, keeping y as a constant, plus derivative of 7x is 7 and y as it is. So derivative of f of xy is 6xy plus 7x. Notation. In Leibniz notation, we write dabba f by dabba x, dabba f by dabba y. In compact notation, we write this form and higher order derivatives written as this. Now let's understand the concept of composite function. A composite function is when one function is inside another. Let's say we have z is equals to f of u, where u is function of x and y, v is also function of x and y, then z become function of x and y through u and v. To differentiate such function, we use chain rule. So here z is function of u and v, and u and v is function of x and y, then partial derivative of z with respect to x can be written as partial derivative of z with respect to u plus into partial derivative of u with respect to x plus partial derivative of z with respect to v into partial derivative of v with respect to x. Similarly, partial derivative of z with respect to y written as this. Say example, if u is equals to f of r and r is equals to under root of x square plus y square, then prove that dabba square u by dabba x square plus dabba square u by dabba y square is equals to f double dash of r plus 1 upon r into f dash of r. So see answer. Here also u is function of r and r is function of two variable x and y. Then u is composite function of x and y through r. So here apply chain rule since u is equals to f of r and r is function of x and y. So first of all calculating dabba r by dabba x and dabba r by dabba y. So r is equals to under root of x square plus y square. So squaring both sides we get r square equal to x square plus y square. So differentiate both sides with respect to x. So derivative of r square is 2r into dabba r by dabba x because here r is our dependent variable and derivative of x square is 2x only because x is our independent variable. So derivative of y square is 0 because here y is constant. So therefore dabba r by dabba x is x by r. Similarly dabba r by dabba y is y by r. Now dabba u by dabba x can be written as dA by u by dA by r into dA by r by dA by x, because u is composite function of x and y. So dA by u by dA by x is equals to dA by u by dA by r is f dash of r, because u is equals to this f of r. So dA by u by dA by r is f dash of r into dA by r by dA by x is x by r. So dA by u by dA by x is f dash of r into x by r. Similarly, dA by u by dA by y is f dash of r into y by r. Now see second derivative. For second derivative, we have to use the product rule and chain rule too, because this function r is function of x and y, and this here x by y is function of x and x. So dA by square u by dA by x square equal to d by dx of dA by u by dA by x. dA by u by dA by x is this. So now here use product rule. This is function of x and this also function of x. So here use product rule. First of all, taking derivative of f dash of r. Derivative of f dash of r is f double dash of r into, again by chain rule, derivative of r with respect to x is x by r, and this x by r as it is. So x by r into x by r is x by r whole thing square, plus next time f dash of r as it is, take derivative of this with respect to x, but derivative of calculating derivative of x with respect to this is here also function of x and r is also function of x. So here we have to use u by v rule of derivative. So this is u by v rule. So our u is x and v is r. So dA by dA by x of x by r is r square minus x square upon r cube. Similarly, dA by square u by dA by, so dA by square u by dA by x square is this. Similarly, dA by square u by dA by y square is this. Now adding both dA by square u by dA by x square plus dA by square u by dA by y square, after adding and calculating, we get this answer. When we perform partial differentiation, we must treat all other variables as constant. So, see, variable to be treated as a constant. For example, if we are differentiating with respect to x, we treat y as a constant even if they are related. Suppose x is equals to r cos theta and y is equals to r sin theta, then r square equal to x square plus y square. So notation, dA by r by dA by x, keeping theta as a constant, written as, or meaning of this is partial derivative of r with respect to x, treating theta as a constant in a relation expressing r as a function of x and theta only. Suppose example, if u is equals to x plus by and v is equals to bx minus ay, find the value of this. dA by u by dA by x keeping y constant, dA by u by dA by x by dA by u keeping v constant, dA by v by dA by y keeping u constant, dA by y by dA by v keeping x constant. So our given u is equals to ax plus by. Firstly calculate dA by u by dA by x keeping y constant, means partial derivative of this u with respect to x keeping y constant is dA by u by dA by x keeping y constant is derivative of x is a, and plus derivative of by is 0, because here b is constant and y is also constant. So dA by u by dA by x keeping y constant is a. Similarly, next derivative is dA by x by dA by u keeping v constant, means we have to write x in terms of u and v. So after calculating, x can be written as v upon b plus y upon a. So partial derivative of this x with respect to v keeping y constant is derivative of v by b is derivative of v is 1 and 1 upon b as it is, and derivative of y by a is 0. Now to find next dA by x by dA by u keeping v constant, means we have to express x in terms of u and v. So we have to write x in terms of u and v. So eliminate y between the given relation. This is our relation u is equals to ax plus by, v is equals to bx minus ay. So we have to remove or we have to eliminate y between these two relations. After removing, means two equation equating, we get after removing, we get x is equals to au plus bv upon a square plus b square. Hence, dabba x by dabba u keeping v constant is derivative of u is 1, a as it is, a upon a square plus b square plus derivative of b, v is 0 because here v is our constant and b is also constant. So dabba x by dabba u keeping v constant is a upon a square plus b square. Similarly, to find dabba v by dabba y keeping u constant, eliminate x between the given relation. This is our relation. Eliminate x between the equation. So after eliminating, we get v is equals to bu minus a square plus b square into y upon a. So dabba v or partial derivative of v with respect to y keeping u constant, derivative of bu is 0 because u is our constant, so v is also constant, so derivative of bu is 0 minus as it is a square plus b square also as it is and derivative of y is 1 upon a. So our final answer is minus a square plus b square upon a. So from equation 1, 2, 3 and 4 on multiplication we get this. Answer will be 1. So geometrical interpretation. Let's visualize this. Imagine surface in 3D. Composite function define surfaces where height depends on x and y. The partial derivative gives slope along a specific direction, say moving along x-axis while y is fixed. And chain rule help us trace how changes in inner function affect overall output. So that was the brief introduction to partial differentiation. It's a small topic with huge applications from engineering to economics, from physics to finance. Thank you for watching. If you like this video, don't forget to like and subscribe. See you in next lecture. Thank you.